Hi everyone. This is your astronomer from Helsinki. Um, and let's get to my file. We continue our work. Did I put it here? I close it accidentally. I closed it accidentally. All right, but here it is. See, you cannot. I'm not sharing it, so you cannot see it. But yes, thank you for joining me. Let's continue our wavelengths calibration. I almost said wavelength celebration because my mind is also in another place. But as you know, I have published several books recently. One of them is Helsinki and Me. Um, and it is available, all of the books are available in as an ebook for purchase on Amazon for $5.99, I believe. And you can purchase them in Europe as well, wherever Amazon sells. Um, and as you know, I create a lot of video content on YouTube about the city of Helsinki. And I'm happy to share that tomorrow, which is the 12th of June, it is the Helsinki Päivä, a special Helsinki day to celebrate the city. And I'm also hosting an online YouTube live event. I'm hosting in an official celebration program event also. And my husband James Don will be uh, uh, collaborating with me to create a nice streaming experience. And I will discuss tips and interesting places to go to visit in Helsinki and interact live, whatever questions come up tomorrow. And I look forward to it. And the whole city kind of opened its arms to various activities, sports, yoga, on various times of the day. I know it is a business working day. It's not really an official holiday. So there are evening activities, different food, exploratory activities, activities for children, outside, inside museums, free museum entrances. And this video right now is from several years ago. I took from the zoo, the local zoo, the Helsinki Zoo. So please enjoy. But now we dive in. And the event is at 11 a.m. EEST, local Helsinki time, tomorrow, June 12th. Join me on the YouTube platform under the live streaming under my channel. So you can choose that. And you can click the notification button so you get a notification or a reminder about it. Okay, so now I will share my screen. It proposed to work. Last time the recording failed. Maybe I forgot to share my screen. I don't know. But we are doing this multi-part tutorial. Last time we dealing with the wavelength calibration. Last time we measured the base-to-base width of an arc emission line, and now we are going to do the next step, which is identify task. I will say it's cryptic solution to pixel versus wavelengths. Lambda. I'll have to insert a symbol somewhere. Insert special characters. the solution to this pixel versus wavelength. And we are going to do it through the identify task. This is where we are. All right. So I'm going to stop sharing on this computer, and I'm going to start sharing on another computer, and I will kill my video. Thank you, the monkey. Thank you, the zoo. All right. No, I don't use the meeting. All right. Okay, so this is my iRef screen. I have my day's research notes open, and actually everything looks well. And last time the video partially didn't work, so hopefully it will work this time. But basically, I will give first a few remarks about wavelength calibration. In this step of wavelength calibration, we are trying to find a solution to wavelengths lambda in angstroms versus pixels. Once we have this solution, then we can apply it to all spectra. We use the helium-neon arc before the target exposure. So we take one comparison spectrum, which is the same as arc spectrum, and we take the central line, and 10 lines are added to that central line. So we extract. We perform the identification with that extraction, and the task used is identify. For example, once we have this central line padded with 10 lines, then we can identify 4 lines, one in the beginning, one at the end, and I'll show you, and 2 in the middle. And maybe let's just already dive in. I might add a graphic or illustration or an extra video to describe in detail, but actually I give the resources of the full documentation, which in great detail explains what's happening with these tasks: identify, re-identify, and fit codes. These are the ones that are used. And you can also read not just the tutorial, but the documentation of the task itself. So what are all of the parameters to identify how it's working? If you want to go, but now we're doing the technical part. We are working with the helium neon arc. Maybe here I said we are working with the helium neon arc frame taken before the quasar 120. So the first task that we are going to do is identify. This helium neon arc has been processed through the bias step, the flattening, and it was also trimmed. Now with the identify task, we identify lines and create a dispersion solution for one line. And for that, we are gonna launch the 2D spec long slit package. So what's happening, I work with 2D frames. So I go to NOAO environment, the 2D spec, and then I use long slit, and I will Yesterday I forgot to copy my steps from IRAP, so I'll try to do that now. So now let's look at the identify task. If are identified, so these are all of the parameters. Now we have to enter the name, and our name of that frame was this one. It ends with 65. Let's find the correct name. And then we will use the middle column. This remains the same. We use 10 to sum with some 10 lines. Coordinate list matching limit. Check the documentation. By this positive 10 here. But why is it negative here? I don't know. I have to check. Chord list. Match minus 3 is the maximum difference for a match between the feature coordinate function value and a coordinate in the coordinate list. Positive values are in user coordinate units and negative values are in units of pixels. Maximum difference for a match between the feature coordinate function value and the coordinate in the coordinate list. Positive values are in user coordinate unit and negative user coordinate units. Coordinate unit. Negative values are in units of pixels. When I'm matching, just leave it because it's pixels, and I'll change in my 50/100 is emissions we're looking at. So here, feature widths in pixels. This one I have to change because we measured the F widths. parameter in the identify tag. This is 9. Centering radius in pixels. Features threshold for centering, minimum pixel separation. Spline. Fine. Quarter of coordinate range. Iterations, lower rejection sigma, upper rejection sigma, rejection growing radius. Automatically write it out. Now graphics output, blah blah blah. So the question I had about was so we have measured the feature width in pixels. It was 9. I decided to put this centering rate to 6. It was 8. We'll see. We can modify it later if needed. So now we actually, I'm going to save this. Now execute it. And here is my I'm plot window with the lines. I click on it to activate it. Bigger. W. All right, so now I have to have my list of lines, and you can find those. And now we have right helium and but I actually printed them for me because it's easier with a printed one, so you can see all the lines here. This is how you access. Okay, so let's do this. So I can type W after I activate the I'm plot window, and then E, and then another E to mark the rectangle for zooming, as in the previous step. So this is I'm plot. task. So let's say we want, and then we can, if needed, click W and A to zoom back out. Let's demonstrate. For example, this tiny little line. I do W and then, so it says window here, E on this corner, E on the top right corner. So here it is, and then maybe again. Okay. So this, to mark a line, now I have to identify this line. I hover with the red crosshairs above it and click M, and then I have to type the wavelengths and then click enter. So let's identify this line. It's the little helium line, 3888, and you don't have to type the full decimal points. You can, in principle, you're supposed to type just approximate is okay because it has a database, but we'll see. So I'm gonna click M. So I brought my crosshairs here. I click M, and then I type the wavelengths. I'm typing it's 8, not 6, 3, 8, 8. They hide loading me. Okay, yes. Okay, here. Now I can see here what I typed. 3888, and then after I type it, then I click enter. Okay, it is identified as my line. Yay, how do I know? Because here it says that this position is 3888.646, which has the correct decimal points, angstroms, and it belongs to helium. Okay, so let's do a few more. For example, so in order to now zoom out, I click WA. I'm zoomed out. I'm just reaching for my other printouts of the old printouts of the emission line maps. Take them. So double check that I identify the correct line. All right. And the trick is also because it's inverted. So on my paper, this little line is on the left-hand side, not on the right-hand side. But okay, let's do one in the middle, like this one. So we do W, E, E, and then like swinging close. And this is this 50151. 5015, enter. And it is a helium line. I guess I can take a snapshot. And then WA, and I'll take another snapshot. Okay. So I did two lines on this side. Let's do another line for, so I did two heliums. Let's do a line for a neon. A good neon line would be this strong line here. for example. The leftmost is 765. It's a helium. Is it? Yes. But then right next to it is neon. Um, and it's 7032. You know, shot. Okay, and zoom out, and let's do one more. Maybe let's do three. Mm. Okay. Think two lines fuse or something here together. I'm not sure. So maybe it's not a good one to identify. So, because there's a prominent line 50A75 in helium, because but I think it gets fused with a neon line, so I will skip it. And then this is neon 5944, for example. I can do this. Um, 5944, and a little one. Yeah. Except that this is a neon one, but we can also mark the helium one in N. It says so that you can do four, 3, 4 lines, but um, we'll do a little bit more because I'm doing a tutorial. Okay. Um, like 2 more lines in this forest of lines. Or go to there's only 46096. Try and then let's do this. The helium. There's helium 4471. Okay, I think we have identified lines in the blue region, in the middle. Here, we are done. I'm not so away. Now we can sniff. And we can check. Next, we check the linear feet. We do column, order 2, and then F. This is a linear fit. Okay, so I did order 2, so enter, and enter, and then press F. Getting some noises in my computer. Okay, so I was playing behind the scene with the feet, so I'll walk you through the steps. Um, let's see. We can start with 2. I press 2 and then F, and actually H. H shows the feet. These are the points that I identified. and the x-axis is the wavelengths in angstroms, and the y-axis is the position in pixels. So for example, this is not exactly on a line. This point is on a line. This one is not exactly on a line. And these three, if you remember, are the sparsely populated blue end emission lines in the blue end from the arc. And this is a red end. Now it's flipped from blue to red. Before it was from red to blue. And these ones also are not exactly sitting, these residuals. These points on the linear fit. So if I click on letter key J, I get the residuals, and you can see that residuals have like a parabolic shape, but we want them to be scattered randomly. So if I click H again, I go back to the fit itself. Then let's increase the order, and the RMS is not good either, it's 26. I'll increase the order to 3. I typed colon order space 3, then enter, then I click F. The RMS is greatly reduced, and I will do J to see the residuals, but I don't like residuals because it's some kind of S. I feel like it's some kind of S here. Not exactly random. Maybe it's okay. And then if I go back, but at least I can visually see that pretty much the crosses are sitting on the fit. The next we'll do order 4 and then F. And the RMS is reduced a bit more. And if I do J, I like this better, these residuals better. Let's look back again to residuals of order 3. See, the residuals also deviate more than 1 angstrom. For example, this point or this point. So I would like to bring it less than 1. So I will go with a higher order than F. So all of my residuals are below 1. And then we can look at this fit itself, and I'll take a snapshot. We can take a look at the residuals with the J key. Let's record the RMS is 0.36. The fit is order 4. And there's also L key, which is another view of the nonlinear component. All right, so now we have everything. It's done. We played with the order. We got the good fit. We didn't need to delete. We didn't have any major outliers. And we checked and recorded the RMS. And now we are ready to actually quit with by pressing. I just keep pressing on it to activate the I'm plot window to make sure it's activated. And then I click Q. It returns to the comparison spectrum. So now you can see that it is from blue to red, and the x-axis is wavelengths in angstroms for the helium neon arc. Thank you very much. I took a snapshot, and then we can click another Q to exit because identification is complete. And this is what the identify task does. Now it says in prompt, write feature data to the database. Yes, we press enter, which means yes. So in parentheses, it meant that the answer default answer is yes. That's why I pressed enter. But if the default answer is, for example, no, then you type yes. So what happened? We can go back to our files. This is a database they're talking about. And here there is a file ID with the arc name. Maybe I'll take a picture and create it. Database directory, file name, this. These are the features that I identified. Some were helium, some were neon. Maybe I will copy paste it here, just so we identified these features. And the order is 4, function Chebyshev, and these are the coefficients for the function. All right, so we are done with this task, and I think I'm gonna stop recording here.